Good morning, everyone. Today I'm going to be doing a tutorial on, let me just switch my face camera on. Is it now? There we go. Okay, good morning, everyone. Today I'm going to be a tutorial on angular momentum and torque and also static equilibrium. Okay, that's what this tutorial session is going to be about. Now, let's see. Okay, let's jump straight into the questions. Okay. Now, Arnold should have done the problems on angular momentum and such. So I'm going to start question 6, or I am supposed to be starting here doing question 6. From question 6, the amplitude of a simple harmonic motion. Yet I don't think that you guys are here yet. Okay, there, this one is the only one on simple harmonic motion, so I will go with it as is. Okay, so let's see simple harmonic motion. Just want to check something here. This is torque. This is torque. There is a simple harmonic motion problem in here that I don't think should be in here, because this is on torque. This is torque, and this is torque, and this is torque. But I will answer that question nonetheless. This one on simple harmonic motion. Yet I do think that it should not be asked yet, because you have not done simple harmonic motion. So I'm going to start with question 7, which has to deal with torque. Okay, let me just then revise my setup. This question should not be here. I'm going to make a note of that. This question is for simple harmonic motion. This is the question where torque should start, question number 7. Okay, if you do want me to do that question, I do have the answers. I worked it out, but I'm just realizing now that is a different section of work. So this is problems on torque. How do we do with torque? What is torque? Okay, now we know that torque is equal to the position vector multiplied or cross multiplied by force. Okay, so position by force. Okay, so here is the problem. A particle is located at some position ij, I hat meter. So the position is I hat plus j hat. I keep forgetting the hat part. That's 1 I hat plus 1 j hat, while the force is equal to 2 I hat plus 3 j hat. Now the talk about the origin is, so this position, let's say this is, I'm going to try and draw it quickly so you can see what it is. This position is somewhere here, 1 and 1. Okay, I and j, this is the j hat direction, this is the I hat direction. Okay, so this position is somewhere here, this is point R. Okay, now a force of 2 j hat, 2 in that direction and 3 in this direction, is on this. So 2 in that direction, in the I hat direction, and then 3 in the j hat direction. So let's say 2 in that direction, 2 in that direction, this will be 1, this will then be 3. So 2 in that direction, and then 3 in this direction. So that's 1, 2, and this would be in the 2. So the force would be this way. This would be that force. Okay, that would be the force. Okay, acting at an angle. Okay, we don't actually need the drawing, so I'm just showing you. Okay, but we want to talk about the angle. So we know torque is equal to position vector multiplied across cross with the force vector. Okay, now the position vector is 1 I hat plus 1 j hat crossed with a force vector which is 2 I hat plus 3 j hat. Okay? This is cross product of vectors, and then you of course you know that R cross F, two vectors crossed, you will find its determinant. So this will be I hat and j hat. Then of course we write the first vector is 1 and 1, while the second vector is 2 and 3. So if we find that it's 1 times 3 minus, so the answer is then this cross product is equal 1 dotted with 3 minus 1, 2 times 1 or 1 times 2, it's the same thing. That is 3 minus 2, so it is 1. Okay, so 1 in the k hat direction, so that's your torque. 1 in the k hat direction, that is your torque. 1 unit in the k hat direction. Now this is torque, and since it's position, which is meter, and then times a force, so it's Newton meters. Okay, so it's Newton meters, so meter newtons, we usually call it Newton meters. Okay, so 1, by the way, it is in kilo. I don't know why they write here kilo. Oh, sorry, it's not kilo, it's k. It's in the k hat direction. It's because it's not a hat on there. Now we go to question number 8. Still a torque problem. They ask you, a torque can be exerted on a body with a fixed axis of rotation. Okay, only by what force? Is it only by a centripetal force? Only by a force directed radially outwards? Only by a tangential force? Only by a force with a component directly radially outwards? And by any force pointing directly toward or away from the axis of rotation? Okay, so if this was the axis of rotation, okay, this is whatever it is that is being torqued, okay, then the force, is it only caused by a centripetal force? No, it can be caused by a centripetal force, yes. The only force that cannot cause a centripetal acceleration, let's say if the force is in this direction, it will cause a torque, in that direction a torque, in that direction a torque, in that direction a torque, it will cause a torque. The only way that this force will not cause a torque is that if the force is directly pointing towards, if the force is pointing directly toward, away from the axis of rotation. Okay, so this E, a torque can be exerted on a body with a fixed axis of rotation by any force. That includes a centripetal force, that includes a force directed radially outwards, by a tangential force, by a force component radially outwards, by any force that is not pointing directly towards or away from the axis of rotation. So if it points away from the axis of rotation or towards the axis of rotation, it cannot cause a torque. Okay, so that will be answer for 8 is E. Okay, number 9. Question number 9. One is quite fast because we have removed the one on oscillation or simple harmonic motion. So question number 9. Consider the force applied to the cylinder as shown. So this is the cylinder looking from the top. Right? Which keys result in a non-zero torque, okay, about the central axis? So if you look at the center of each circle, that will be its pivot point. Okay, now force A, okay, if you were to apply force tangentially to the circle, it will create a torque. Now if you were to apply force in the direction of B, there will be no torque because it's directly towards the center of the axis of rotation, so no torque. For C, this is where I have a problem because it depends slightly. Well, let's go first F, no torque, and then force D, no torque, And E also no torque because it's pointing either away, radially away, or directly towards the center. Here, it's this law. It is forces are pointing directly towards or away from the axis of rotation. This one here in C, that force should be moved a little downwards, so it is pointing directly away from the center, okay, or angled slightly. That leaves only force A. Okay, that leaves only force A. That will be a non-zero torque. Question number 10. And this will be our last one for today. Okay. A horizontal uniform meter stick. Okay. So a horizontal uniform meter stick. Supported at the 50 cent mark, has a mass of 5 kilogram hanging from it at the 20 centimeter mark and a 30 kilogram mass hanging from it at the 60 centimeter mark. Determine the position of the on the meter stick at which one would hang a third mass to keep the meter stick balanced. Now, we know M1, okay? Mass 1 is a 50 kilogram, a 0.5 kilogram mass, and it is at the 20 centimeter mark. So it is at the 0.2 meter mark. And then we have mass 2, it is a 0.3 kilogram, 0.3 kilograms, and it's hanging at the 60 centimeter mark, so the 0.6 meter mark. Okay? Now we know for it to be in equilibrium, this meter stick, the torque, the sum of all the torques must be equal to 0 for it to be in equilibrium. Okay? So let's say this is the meter stick. So let's say the pivot point. So let's say X pivot. The X pivot point is at 0.5 meters. So at the middle of the stick, in the middle of the stick. Okay? And then we have some sort of mass M3, and we don't know what it is and at what point it should be at some distance. Okay? That's why we're going to have to hang mass M3. Now, the condition is that the sum of all the torques must be 0. The pivot point is in the middle. We have some mass at some distance to make it correct. Now, the torque due to M1, okay, M1, the first mass, the torque due to M1. Now, first, the torque due to M1, the torque due to M1, okay, that is R1. Well, first we must find the position where it is, okay. They tell us it is at the 50 centimeter mark. The pivot point is at the 50 centimeter mark, and then at the 20 centimeter mark there is a mass hanging. M1 is hanging at a 20 centimeter mark. So we calculate the distance from the pivot point. So it's going to be x1 minus the pivot point. X1 is the 20 centimeter mark, so 0.2 meters. That's x1 minus the pivot point direction, so xp, that's 0.5. That gives me, let me see if it shows up on the computer there. That gives me 0.2 minus 0.5. That is, you can still see, that is negative at 30 centimeters. It's at 30 centimeters. So it is at negative 0.3 meters. Okay, so negative 0.3 meters, it means it's on the left hand side of the pivot point. Okay, so at 30 centimeters, so it is from the pivot point. Remember, we always calculate the distance from the pivot point. Okay, this 20 centimeters tells us where on the meter stick it is, but it does not tell us the distance from the pivot point. Now, the pivot point is halfway through at the 50 centimeter mark, and then the first mass is hanged at the 20 centimeter mark. That means there is a 30 centimeter difference between the pivot point and the first, where the first mass is hanged. So that is the distance r1, and then the torque then would be r1. The torque would then be equal to r1 times the force created by the first mass, which is m1 times gravitational acceleration, which in this case it is 0.3, negative 0.3, which is the distance. The mass of m1 is 0.5, so 0.3 times 0.5, negative 0.3 times 9,8. Remember, the weight in this case is the force, and that gives us negative 1,47 Newton meters. That is the torque due to the first mass. Now we do the exact same thing for the second mass. First, we calculate what is the distance that the second mass is hanging from the pivot point. Okay, where's the pivot point? 0.5. Where's the second mass hanging? At the 60 centimeter mark. So R2 is equal to 60, or 0.6 minus 0.5, which is the pivot point. So it is a distance of 0.1 meters away. Torque due to the second mass is R2 times mass 2 times G. That is equal to, the distance is 0.1 meter, the mass is 0.3 meters, and then of course we have 9,8 meters per second, and that gives us a torque of 0.294 newtons per meter. 0.294. That is the torque that is generated by the second mass. So now we have two torques from the two masses. Okay, now we know that the sum of these torques must be equal to 0. By the way, I forgot there's a negative there. So we know now that the sum of the torques, because that is the condition for equilibrium, must be equal to 0. So negative 1.47 plus, that is Newton meters, I write there Newton meters, plus 0.294 Newton meters, plus some distance away. Okay, this will be some distance r x3 minus the pivot point, that will be the sum distance, multiplied by the weight m multiplied by 9,8. Okay, this is exactly the same as we did the others. Okay, this is now for torque 3. This is the unknown torque. This is the unknown torque that we should also add, and then it will all be equal to 0. Okay, now if we were to, this is 1.47, if you were to add all of that up, you can just now and then solve for x3. Okay, if you were to solve for x3, let's see, it will be x3, which is the distance away, minus 0.5 times the mass times 9,8, and that should be equal to 1.47 Newton meters plus 0.294 Newton meters. Okay, that gives you 1,176 Newton meters. And if you divide on both sides, that will be x3 minus the midpoint times m times 9,8. Okay, now if you divide both sides by m divided by 9,8, you get that x3 minus 0.5 is equal to 1,176 divided by m times 9,8. Therefore, x3, if you take 0.5 over negative 0.5, it becomes positive 0.5. It'll be 1,176 over m times 9,8 plus 0.5. Therefore, if we continue to calculate, that divided by 9,5 is just 0.12 over m plus 0.5. Now if we were to write this is in meters, so the distance, they ask us determine the position that the meter stick, so we want that x3, but this is in meters, so if we were to do it in centimeters, we'd multiply all the lengths by 100, so it'll be 12 over m plus, that will be 50 centimeters, so 12 over m plus 50 centimeters, that will be the distance. 12 divided by the mass plus 50 centimeters is the position where this new mass will hang, and it's 12 over m plus 50 centimeters. And that, ladies and gentlemen, is the end of our session. It seemed it was very quick because I removed, for some reason, I don't know, still don't know why there's harmonic motion problems in here, but we have done everything we should have, and I thank you and all the best. Thanks for tuning in.